Today our topic is all about the energies of electrons. And so what we're going to do is we are going to calculate some energy changes. So calculate the change in energy of an electron if it drops from quantum level 6 to quantum level 1, which is its ground state. And then what is the wavelength of the energy that it emits once it, as it's dropping from quantum level 6 to quantum level 1. So in a very simplistic view, if this is our nucleus and we have 1, 2, 3, 4, 5, 6. Okay, here's quantum level 6, here's quantum level 1. Okay, and we've excited an electron to the point where it's energetic enough that it can hang out in quantum level 6. Okay, it's going to jump now back to its ground state. Okay, so it's going to go all the way back down here to quantum level 1. And in the process, of course, in order to inhabit quantum level 1, it doesn't need to be nearly as energetic. And so it's going to emit energy, and what we're asking here is what is the wavelength of electromagnetic radiation that is associated with the amount of energy that it's emitting. Okay, so we will use an equation for this. That is, energy of an electron is equal to negative 2.178 times 10 to the minus 18th joules times z squared over n squared. All right, E is the energy associated. Okay, this is a derivation of E equals hv. Okay, so it is a simplified, rearranged version of E equals hv, which is Planck's constant times the frequency of the wavelength. Okay, so what is Z? Z is equal to the nuclear charge. And the nuclear charge is simply the number of protons within the nucleus. Okay, and what is N? N is an integer describing the electron quantum energy level. Okay, so N is basically what shell is the thing in. What quantum level is the electron in? Okay, now we're going to begin this by simply just saying, okay, how much energy does the electron possess at quantum level 6, and how much energy does the electron possess at quantum level 1? Okay, and I did not make this very clear. This is a hydrogen atom we're talking about. Okay, this is a hydrogen atom. We're making this very simple. So what is our nuclear charge going to be? Our nuclear charge is going to be 1 because a hydrogen atom just has a single proton. Okay, so let's do this thing. So let's figure out how much energy the electron possesses at quantum level 6. So n equals 6, principal quantum level 6. All right, so we're going to say the energy is equal to, I do not have this number memorized, negative 2.178 times 10 to the minus 18th. Okay, we're talking about a hydrogen atom, so our Z value is going to be 1 because there's 1 proton in a hydrogen nucleus. So we're going to have 1, okay, and that quantity is going to be squared, but 1 squared is 1, divided by, if we're talking about quantum level 6, okay, 6 squared. Okay, and we end up having a value of negative 6.050 times 10 to the minus 20th joules. And let's figure out the amount of energy associated with an electron at quantum level 1. So when n equals 1, we'll say negative 2.178 times 10 to the minus 18th. And again, we have 1 proton in the nucleus, because it's hydrogen, and we are at quantum level 1, so 1 squared. So this thing is equal to negative 2.178 times 10 to the minus 18 joules. Okay. Okay, this one has more energy because it's less negative than this one. Okay. Now, so if we do this, we can say then the change in energy is equal to the final minus the initial. And so the final is going to be negative 2.178 times 10 to the minus 18th minus negative 6.050 times 10 to the minus 20. Okay, that's going to be the change in energy, or the energy that is going to be emitted by this electron. So our answer here turns out to be negative 2.117 times 10 to the minus 18th joules. All right, so it's a negative value. That means it's exothermic. So energy will be emitted, which shouldn't surprise anybody. And of course, with that energy being emitted, we have a more stable electron. Okay, so this is the amount of energy associated with that electron going from level 6 to level 1. It is exothermic. It is emitting the energy. Now, we could have also done this thing. We could have skipped this step and kind of condensed it all. And to condense it, so first of all, I just wanted to show it to you this way so that you know, well, if you have to calculate the energy possessed by an electron in quantum level 6, could you do that? Okay, now, in terms of the change, you could do this all in one step, you guys, by just simply saying E equals negative 2.1178. Oh, you can take the box. I don't have any food in it, unfortunately, but you're just going to take the box? Okay. so we'll just begin with the same, but then we could just simply say, in parentheses, z squared over n squared final minus n squared initial. Okay, so we could do it all in one step if that's what we needed to do. All right, so let's go back to the job at hand. So we know how much energy is associated with the electron dropping down to its ground state. So what about the wavelength? How do we figure out the wavelength of this thing? Well, lambda is equal to, and lambda's wavelength, hc divided by our change in E. Okay, so lambda is wavelength, h is Planck's constant. So we'll take Planck's constant, which is 6.626 times 10 to the minus 34. And we're going to multiply that by the speed of light. And of course, this is going to be in meters per second. So 2.998 times 10 to the 8th meters per second. And then our change in energy associated with this was negative 2.117 times 10 to the minus 18. So negative. Okay, now we use the absolute value here because we say that the energy is emitted. Okay, so we know that if the energy is emitted, we know it's negative, but this is going to be an absolute value. We don't want to come out with a negative wavelength. Okay, so if we do this calculation, you guys, we end up getting a wavelength that is equal to 9.383 times 10 to the minus 8th meters. And then if we look at the electromagnetic spectrum, we find that the energy that is associated with this wavelength right here is ultraviolet light. So we would actually not even see this emission. This emission wouldn't even be visible to us because the wavelength is UV. All right, that's how we find the energy of electrons.